And welcome to our panel that will discuss materials, a topic that is super interesting for me. Material news in aerospace, metals versus high-performance polymers. There's always the discussion when to use metal, when to use high-performance polymers. And this is, of course, something that will evolve in the future. And to discuss these topics with me today are three fine gentlemen from the additive community. David Sanchez Wells, a Director of Technology and R&D from INDAERO GRUPO EMERGY. I hope I said it properly. Suraj Rawal, Technical Fellow at Lockheed Martin Space. And Chris Crowley, Enterprise Team Lead from Formlabs. Welcome, all of you.
Thank you, Gil.
Just to let you know, we'll add Suraj soon. We think he might have just stepped away for a moment, but we'll add him on very shortly. But continue on.
No problem. So I think the best thing would do to start with a short introduction by each of you. David, maybe we will start. If you can describe what you do, how you relate it to additive, so we know where to.
Great. Well, at first, I would like to give you thanks for inviting me to this panel. I think it's an interesting topic. So I hope that we are going to generate a value for the viewers today. We in INDAERO are a small manufacturing company based in Seville, which is a city closely related to the aerospace sector in Europe, as many of the military aircraft that Airbus manufactures come from a company that was based here in Seville before becoming part of Airbus. And well, our company is focused on using plastic materials for the products that we manufacture for Airbus. These materials are cellular but compact as well, and we use machining and thermoforming processes for manufacturing these little products. So when the additive manufacturing began to step, to have a stronger step, we decided to get into it so we could be a reference to our clients here in Spain and South Europe in additive manufacturing. So we did acquire a machine, FDM plastic machine with Ultem 1985 as material, as aerospace grade material, and began to offer this service to our clients. So from the first steps of this becoming popular of the additive manufacturing. So with the years, we got the expertise that we have today in this plastic and using this plastic, but at the same time, we discovered that the clients didn't have the necessary knowledge to distinguish when to use this additive manufacturing or not. So sometimes they tried to use additive manufacturing for any reason, and they didn't have the necessary design or the necessary feedback from someone who was able to get the best from the technology. So it really makes sense to do this.
David, we'll just dive into this in our discussion, okay? So just, okay, thank you for that. No problem. No problem. Thank you for that. I think, Chris, you have a different perspective, right? You work at Formlabs, which is a manufacturer, and you are more connected to your users, right? So you feel the aerospace from different angles, different customers.
Absolutely, yeah. So if you can see my slideshow and hear me, we can just confirm that. So yeah, so my job at Formlabs is basically working with our federal defense and aerospace customers, and we're an OEM, but we also distribute and support our products directly. So we do get to interface with a lot of customers, and I'm going to show you a couple of applications where a high performance polymer will be used in aerospace kind of instead of metal, almost like as a direct replacement or in a place where metal is just not necessary. So our company at a glance, our job, we're just trying to make digital fabrication, really for us, it's 3D printing, just easier to use, more accessible on a distributed scale. We want to make it more robust, simpler to install. This is a big, blocker traditionally with industrial, difficult to use machines that are typically needed to make high performance polymers. So we just turned 10 years old as a company. We've bit. I started here 5 years ago. We were about 200 employees, so we have grown quite a bit. We have made more SLA printers. We made more SLA printers in our first 5 years than had been made all time prior because of our smaller form factor and accessibility. So at a glance, our company. Our equipment is two types of technology: SLA resin printers and powder polymer printers. So it's all polymer printing. None of it is filament or metal based. We do have some automation and post-processing, but we also make our own materials. And what really focus on is making a lot of different advanced materials for our printers to accomplish lots of different things for different customers. So we're going to focus on the ones that actually have an impact in aerospace and defense. And these would include glass-filled polymers. We're not the only company that makes reinforced polymers for our printers, but glass-filled polymers have an advantage in they're very stiff, and they can handle higher heat than most thermoplastic materials used for 3D printing. So we see them replacing metal parts where molds would need to be machined out of aluminum, whether you have to send those out, very expensive and time-consuming process to machine aluminum or steel molds. You can run short-run molds for thermoforming, injection molding, composite mold making, silicone mold making, and silicone mold making comes up more than you'd think in aerospace and automotive and ship maintenance parts. What we're actually trying to focus on as a company, or that we like to shift the focus to, is the 3D printing part doesn't necessarily need to be the end-use part. So when people traditionally think about a 3D printed end-use part, what we try to shift to say is, how can we actually help a traditionally manufactured part reduce the cost of producing a part in that scale, which in aerospace, it's a naturally smaller scale, much smaller scale than automotive. So the production runs are shorter, and the cost in that smaller production run is much higher to cut tools for. So if we can help get past that, then we offer some value with our performance polymers that can do more than just be the part itself. Another application would be high stiffness parts that would go in a wind tunnel. I will concede this is relatively low speed wind tunnel at hypersonic speeds. It kind of has to be metal because it gets very hot. The glass-filled polymers is suitable for that. And if you compare it to some of the materials that you'd see, we're getting close in stiffness to some metal manufactured parts, even just off of the printer with a polymer printer. Fiber-filled plastics are terrific. I'll admit that those have better ductility and robustness than some of our stiffer parts. Carbon-filled plastic is another example of a high-performance polymer that can be used to replace metal in some places. So these are some basic applications. I already mentioned the first two, but also structural stuff, bracketry and things like that. They don't need to be machined out of aluminum. There are SLS materials that offer some higher performance, again, reinforced polymers that can do more than we would expect with a traditional polymer. Glass-filled SLS parts. Another new exciting material is ones that can have a particular property of need, and one of these would be an ESD material that is ESD safe for packaging, jigs, and fixtures that traditionally people are machining aluminum parts. I can just get to the next slide. Machining aluminum parts that have all of the problems with outsourcing or even insourcing to your machine shop with cost and turnaround time, saving hundreds of dollars in either production or manufacturing jigs and fixtures, aids like that. Jigs and fixtures, places where parts are being used to help make parts in aerospace are another great application. And even we've seen customers who can electroplate a tubular or a topology optimized lightweight structure with metal over a polymer part, and it can actually outperform either functionally as antenna parts or structurally outperform DMLS aluminum. Like we have seen data to support that it would produce that. So I'll stop right there and let us go back into discussion and keep moving.
Okay, just a general question. Out of Formlabs customer base, how much in percentages, if you know, is aerospace?
So the market's hard to measure globally. I know in the States, it's on the order of mid to high single digits with aerospace. If you combine all of like government and aerospace customers, given that we serve lots of markets from jewelry to dental, it's actually a decent portion because we serve so many customers globally in engineering and product design and things like that.
Cool. Okay, and one more question about the electroplating. So Formlabs is in plastics. The connection for you for metal is the electroplating used by your customers, right, to get the advantages of a plastic part with some characteristics of metal, right?
Yeah, for sure. So this is kind of like a composite part effectively when they do this. And there's EMI shielding, structural, conductive, antenna applications that can come with electroplating. But yes, the basic part is actually a polymer, but the outcome is metal-like performance. And we actually do have a full white paper on this, on comparison of not only to traditionally manufactured metal, but also comparing to directly added manufactured metal, which metal printing is very expensive and very difficult. And if you have a very low cost and easy to use polymer printer that can perform like metal, it really makes it so more people can actually leverage the benefits of additive in design complexity and performance characteristics.
Cool. Okay, so if we go back to the topic of our discussion, and I would like to approach this from the material side, David, if you can follow up on this, what makes a material attractive for a space application? And David, do you have some experience with plastic and metal as well? Can you give us your perspective on how you see plastic, on when do you choose for your customers to use plastic and when metal, and the pro and cons of each? And if you have an example, that would be
well, in our case, all the studies that we performed, every time that a client wanted a product to be studied in order to determine if the possibility of manufacturing, if with additive manufacturing has sense, we determined that using metals in these occasions was not a cost-effective solution at all. In the cases that we have studied, nearly all the cases can be solved using high-performance plastics. Even, for example, one of the questions that someone was making right now was about how do the high-performance plastics last in space. And we have even manufactured plastic structures for satellites, and they are in the space right now.
From which material was that?
Using ULTEM.
Okay, interesting.
Yes, there's even a research article that may be found online. It is public. And well, this company wanted to test and deploy a satellite using these materials as the basis for the structure. And using this as well as metallic normals and a machining process for the tight tolerances zones, the product is perfectly working right now.
So if we take the satellite as an example, so using ULTEM, because it was easier maybe to use, it's lighter than metal, right? The production process was maybe easier than metal, right? So I think it's a clear case where it's obvious when to use plastic than metal, right? If you want to assemble it on the satellite, you need the weight to be as light as possible, etc. But the mechanical properties were good enough, right, to
they were
in the mission.
Yes, and the metal additive manufacturing, from our point of view, talking about some, we have to be clear that the process is not only the material, but the process is a key characteristic too. And usually the metallic parts that are talked about are using SLM technology. And this technology is based in powder, and the powder has the problem of the porosity that under vibrations has like fractures inside. So there are methods to make this effect less important, but at the same, it is an important fact to be taken into account. With this FDM manufacturing, for example, you don't have that problem. Other processes that use solid materials as a basis, like using wire, for example, are looking after reducing this porosity effect. But, well, these technologies are more recent, and at this moment, they are not very standardized as the other technologies are.
Right. On the process side of things as well, I mean, polymers are such a wide category. There's a lot of different ways to make metal AM parts. There's also lots of different ways to make polymer parts. So definitely you would see a different part performance, voids in the part and things like that, differing from filament versus resin laser printing versus powder bed fusion like SLS or MJF printing, where you know, one part might have outstanding X and Y characteristics from continuous fiber, like basically a fiber loaded part from an FDM part might be comparable to metal, but only in a certain geometry, and only certain parts can be made that way. And then glass reinforced polymers that are made with SLA are fully dense. There's no voids in those, although I just saw a NIST study at AMUG that talked about how some of the projector technologies don't necessarily cure everything exactly the same way on each layer, but for the most part, SLA parts are going to be fully dense. And as you start to add glass filler or filler that causes things like the ESD properties in some resins, then the part is actually less polymer in the example of the glass filled. So there is a upcoming study that will send parts to space from NASA on a SpaceX launch to bring parts outside the ISS and the International Space Station and test their exposure to space. And the polymer that they chose was specifically a highly glass-filled polymer, that rigid 10K polymer, because it has less polymer and has less likelihood of being affected the same way that a polymer would, even though it's still a polymer printing process. So there's process and material selection that really comes into that when you're talking about replacing something that would be maybe a metal machined fixture or a metal printed part, but doesn't need to be if the properties are okay with the polymer part. It's like anything in additive, it depends. You could say it depends and cast out any argument.
Right. And Chris, if your perspective of comparing polymers to metal, of course, comes from the customers, and from your perspective, they have different technologies of metal, right? Not Formlabs, and they have your polymer technologies. When maybe you have an example of an interesting case where your customer for aerospace application, of course, chose a specific polymer and not metal for a certain reason, right? Do you have a specific example to share with us that could highlight the differences between polymers and metal?
Yeah, for sure. I mean, there are plenty. I mean, there's a couple of them I can think of. One would be relatively early stage companies getting into space, becoming a space or an aerospace supplier, whether it be for aircraft or actually launching into space, where they don't have the infrastructure or the capital to actually acquire metal 3D printing, but they do need production parts. It's too expensive to have it in-house, or it's, you know, physically hazardous to their scenario, or outsourcing the parts at the volume they are just becomes too expensive, and they go through a decision-making tree for probably every single part on their CubeSat or their little or the part that they're launching out into space, and they can see which ones are actually going to be undergoing dynamic load, because some, you know, polymer parts will be very strong in static loading, and it won't has to bend or flex or anything like that, and that's where a metal performance might make more sense. Coefficient of thermal expansion has to do with it too. So like parts that expand or contract, the more polymer there is, the more they're going to change shape. Aluminum, as an example, is one that just doesn't do that. So or has a much lower coefficient there. So it's a decision-making process. Sometimes it comes down to cost, but we had one of the panelists from an earlier one, very impressive at NASA Marshall. They actually use SLA printing to teach failure modes and prototype metal parts that will later be made on a metal additive solution, so that they don't have to waste all the expensive materials, time, and processes to actually run a metal part. They can have people learn or even test parts printing in SLA because the failure modes are similar. And then they actually are fully planning on making that as a metal part when they either scale up, go to production, or just decide they're actually going to make it on metal for the functional test. but polymer printing helps them all along the way and can serve as kind of like an analog for that testing. And I mentioned the wind tunnel part as well. Hypersonic wind tunnels and wind tunnel parts that will undergo the speed, they're actually cold wind tunnels, but the parts will actually undergo extreme heat in their actual production use case. So there's different choices that happen at different stages of development and production based on metal versus polymer.
Cool. Okay. When we talk about applications for aerospace, you spoke about materials, of course, and the differences of metal and polymers. But at the end of the day, there is a need to qualify the parts. It was discussed in the other panels. But from your perspective, David, when you go through, you know what? Maybe you can share with us some information about how long does it take to qualify a part? It starts, I assume, with the material. What is the process in general for us to understand? Because if you want to, it's an easy example. If you want to print something with PLA, right? There is no qualification. It's a prototype. You do it even at home. It's an extreme example of printing a prototype with no need to qualify anything. I think aerospace is on the other side, right? Where you need to go through a thorough process of qualifying. Absolutely. Share with us a little bit, how does it take 1 or 2 years or?
No, in our case, the first time that I can talk about a specific case, the first time that we found that we received a technical drawing indicating parameters for the 3D printing process is a moment when you become very happy. Yeah, as you can understand, because you have been fighting for after this. And in this occasion, this client asked us to qualify the process, and we considered 2 options: just qualifying this lot, the lot that we were going to manufacture for this client, and qualifying the process itself. In both cases, just using a tensile load test and printing different proofs in different positions, we could make just a tensile test and qualify this lot, for example. So, and this way you can get some security about how these parts are going to perform, or if they are going to have the performance that you are waiting from them from the technical data sheet. So in our case, every time that we needed to qualify the products, we didn't have any kind of problem. It is just the normal cost that you will assume for serving a qualified product, but with no difference to other processes, like machining, for example. If you need a machine part to be qualified, you have to do the same.
And prior to the qualification of the parts, there is a process of qualification of the material. Am I right?
Yes, but the parts themselves, the qualification of them, this didn't have to be performed by us. We just had to qualify that the parts were manufactured according to what our client needed. But the part itself, the client would need to mount it anywhere and do their own tests.
Cool. Yeah. And Chris, yeah.
Yeah, I can add that, like I said before, it's like kind of the easy bailout for anybody in 3D printing is you can kind of say that it depends. And there's parts that are identified as, for example, like flight critical parts, or parts that are like, imagine a switch or a lever on the cockpit of an airplane versus something that's holding the landing gear in place. So like certification process is going to change for those. You go back to the material certification, like you said, definitely, everybody knows Ultem is one that, like a version of Ultem is certified in the eyes of FAA, but there are qualification processes that differ by agency or part of the government. There are very well staffed and capable AM part certification organizations within the Defense Department, for example, that their job is to quickly vet and approve or disapprove 3D printed parts, and even categorize them as flight critical, not flight critical. This can be made out of this material, that material, this process, and they make full-blown data packages for how to make this the right way, when you can make it, what aircraft you can put it on. And so that really is highly part dependent. And as a very well informed gentleman here at the place here, Mike Pacoda, has told me, is that there are parts that could be made out of Skittles if you just made them right to spec, because they're really not going to hold the aircraft up in the air. They're something that is basically alleviating a supply chain problem, and obviously that's a place where polymers, at the cost and complexities, make much more sense to produce than metal. So parts get certified different ways. Some of them that go into components, I mean, it took 5 years to write the entire process for even informed instructions for use for metal powder bed fusion in the military. I mean, I imagine several new technologies within that category even developed in that amount of time. So there's lots of moving parts, and it really can take a long and a different amount of time for something to get reviewed in the eyes of the FAA from a materials perspective. You do have to come back if it's going to keep the airplane up to get the actual part approved. Even if it is a simple part in some cases, like if it's going on a commercial aircraft, you know, the cup holder has to go through a much more rigorous flame, smoke toxicity review than some parts on other types of aircraft or even going into space.
Chris, when we're talking about the evolution of additive, of course, when you look at the whole segments or industries, it's different in dental, right, and automotive and aerospace. But when you look specifically in aerospace, how do you see additive evolution in the next 3 or 5 or 10 years? Where do you think, how far do you think additive can take aerospace in the future? And what would be the main reason for acceleration? More materials, better technology or faster technologies? There's always in specific segment one hurdle or a certain bottleneck that prevents additive to evolve. What do you think in aerospace is the main factor for that?
Yeah, I do think the certification of materials and processes and individual parts is going to be a slow process as we learn and take bumps and bruises from what works and what doesn't. Hopefully, nothing where there's actual like serious like risk, loss of life, or lower on the totem pole is like really expensive stuff that breaks. There'll be more confidence and more adoption. There have been instructions for use and standardized accepted practices that come with more engineers entering the workforce who've been exposed to additive manufacturing, where I would say like the old guard really focused on subtractive manufacturing because I know exactly what this is. I'm going to cut it out of a block and I know exactly what that block is made of. Well, right. Much more kids coming out of engineering schools are going to aerospace engineering, mechanical engineering, are being exposed to 3D printing and not being trained as machinists, learning how to cut a tool path. The machine with the 3D printer plans its path itself. So as more people come in having been exposed to it and accepting of new technology and the speed of development required to be competitive now that commercial folks are going into space, that's really going to help drive it because there's going to be more educated people about what it can and can't do. There was a great article came out here from the Naval Academy where they're teaching our naval officers, the people who will be saying yes or no to budgetary decisions down the road, are being trained in what additive can and can't do. 20 years ago, not a single one of the officers going through school was trained on 3D printing unless they got into some fancy program and learned about what a $500,000 machine could make, this little brittle part, and it was useless. So the education is going to really help with that. So that more people are accepting and willing to start integrating it into what they're doing. I think it plays a huge part, and aerospace specifically has a better chance, I think, of this being successful.
Chris.
Sorry, go ahead.
Sorry, I'm really sorry. Just want to let you know, even with a bit of a delay, we have Mr. Rawal with us for the last 11 minutes of the panel. So I'll let you guys continue. Thank you very much.
Well, let's Suraj.
Sorry for stopping you, Suraj. We have 11 minutes. We will leave 5 minutes for questions, and we'll give you the stage for 6 minutes. Sounds like a fair deal.
I really want to apologize first, but be that the case, I'm from Lockheed Martin. I'm one of the technical fellow involved in material structures and all the other stuff. I was lucky enough to be the first person at Lockheed Martin to fly the 3D printed part up in space which are flying around Juno spacecraft, Juno's around Jupiter right now. So you tell me, Gil, the questions, or should I just tell what do we do at Lockheed Martin?
I think, yeah, at this point, I think if you have 5 minutes, it's interesting for us to know, of course, from what you can share, what Lockheed Martin is doing with additive, specific applications, things that you can see that's happening now and might evolve in the future. If you can give us a short summary of that, that would be interesting.
I can do that, sure. I can take 2-3 minutes and chat. Like every other company, we do small polymer, big polymers, small metals, big metals. And when it comes to, we have all sorts of machines, and also we work very closely with many of the suppliers, all the additive manufacturing, be that EOS or be that RCAMs or be that all the other machine manufacturers and all that. When it comes to using what metals, most of the parts which we make are used in whether small or large, are a lot of work is in tooling. Make, composite tools or metallic tools for the different products and all the other. Then the other area which comes up after tooling is making prototypes. And we make a lot of prototypes to do all the other work and all the other. Then sometimes some other risk reduction elements and all the other. And then we make some production parts. So in the production parts, like for F-35, we fly a good amount of polymer parts over there. About 6,000 of them we do fly. And when it comes to metallic parts, we have flown Inconel's 718, Inconel 625. When we have flown Tice 64, both on Juno, and we have, when it comes to polymer, we have flown polycarbonates, nylon 101, and then Ultem 9085 type of parts and all the others. So the biggest challenge which comes to us is many of these parts are secondary structures, secondary or tertiary structures. When it comes to the primary structure, you have to go through rigor of qualification and testing and everything else. So there we have a lot of challenge. So we have qualified certain powders which we get, the source of the powder, the composition, the specification which come with it, and then the machine which has to be going to make it. So when it comes to the qualification, the challenge comes up. Many of these metallic materials have anisotropic properties. There are low Z and high in-plane properties. And how do we, when we do the, I will say, qualification and what design allowables we should use, that becomes a challenge. But in polymer, it is far more simpler because, but again, even in that one, we have noticed at the fiber orientation at which the deposition is being done does affect the properties and all that. Going to the other question which you asked about, what are we going to do in future? Along those lines, I think our first continuous effort is to understand the basic science and all these integration, because the machines are changing every Friday. It feels like that. When are we really going to converge into in-situ monitoring and in-situ mention the defects and any anomaly in the melting and all that we can capture in-situ? That will help a lot. Because otherwise you have made the part, then you have to go to the all sort of X-ray analysis and everything else along that line. So basically along that line, then the question comes up, that is, how are we, then our interest is also into ceramics, into electronics, 3D printed electronics. We do use a lot of composites in our spacecraft to make it lighter, and even in the other vehicles along that line. Then we are trying to make some precision optical components. And we are also looking into ceramics, can one make 3D printed ceramics and the quality of all that. And as you know, the emerging materials like high entropy alloys, which people are talking about high temperature, because there are certain applications where we do need or we do use high refractory metals, like niobiums and tungstens and all that can be 3D printed along that line. So I've shown you different areas, and the challenges remain always in qualification and basically making sure very good getting reproducible and reliable part every time. So with all that said, I think the challenges are same as we move, because in polymer, the challenges are far less compared to metallics. So any questions along that line? If I missed anything, I don't want to take the rest.
Thank you for the intro, and you touched something that is relevant, which is the ceramic. And there is a question here. We have Philippos. We have 5 minutes, right?
Yes. Well, I'm just jumping in to let you know, Gil, that we've approved the 5-minute extension to the panel, given the Suraj joining. So you have your full Q&A. You can go 5 minutes over. Enjoy the rest of it. Thank you.
Perfect. Thank you, Philippos. So I think the first question is, when it comes to the certification of parts, what are the differences between ceramics, polymers, and metal? Is there one that is easier to have qualified? Interesting one. Who wants to take this? Who has experience with ceramic?
Yeah, I think the ceramics will be far more tougher. I mean, at the outset, I can see maybe in the RF area where we can use certain ceramic, which are RF components and all the others. But again, there also, with that antenna, you have to apply some conductive inks and all the other on those parts. And I think metallics will be far more simpler to qualify. But the problem in the larger picture is the process parameter interdependencies of the machines and all the other parameters. I think we do have some understanding, but the question the designer asks is, we have flown this part many times. Is your part as good as the one which you have flown every time? So what we call the technology readiness level or manufacturing readiness level, are we there yet? In some cases, we have done it. But going back to the basic question, I think metallic will be simpler or easier than ceramics. Maybe that's how I can say.
Okay, interesting. David, maybe you take the second question, and then Chris. David, when it comes to end-use parts, would you prefer using polymers or metals? I assume it depends on the applications and the requirement from the customer.
Yeah, it basically totally depends on the application.
Sorry, Suraj. David will take that.
Yes, but Suraj is totally in the knowledge that the application is the key fact of determining which material and which process to use for each material. This is a key fact too, because using FDM or using SLS can have quite different consequences in reference to qualification process, for example, or probability of failure. Because the way that the parts fail is totally different.
I think the main factor is when I go to service providers, right, and they have all kinds of technologies. So it's not that you have, I don't know, SLS and FDM, and you try to cover all applications in these two technologies only because this is what you have, right? So ideally you have all technologies, and then you say, and then you ask the customer, what does he need? Right? There is a list of questions and to understand exactly what they need, and then you pick the right technology and the right material, right? Not vice versa. So
the real challenge is to have the knowledge to be the best decision maker for choosing the material, position of printing and technology and everything, every aspect to be taken into account to say, okay, I need specifically. But if you look at any image of the 3D printing ecosystem with the materials and the technologies and fathers, children, there's an image about that. It is a huge subject. So it is not so easy to find a specific manufacturer who is going to tell you this is the process and I have it. They will choose the best fit that they have in-house, but the best technology, maybe not.
Exactly. Chris, what type of materials do you see in the future? Maybe one or two that can be used in aerospace that are not used today. Do you have some materials in mind that you see relevant or necessary or coming in the next few years?
Yes, I think it kind of depends. Like, are they here or are they here in the right places in an accessible place? There's filling materials with performance characteristics, for example, filling a part with a scintillant, like radiation detection part, right? Like it's almost like a 4D printed part. There are, in another example, like conductive materials, things that can actually do more than just be a physical part taking up space, I think are really important. I think that coatings, like we talked about, like plating and coatings, are going to be really important to get the advantage of a certain print process or material, but basically protect or encase the part from the one flaw that it has in terms of chemical or UV resistance, where like I really like what this material can do, but I actually can't put it where I want to because of the environment. That's definitely a big area of improvement for additive manufacturing, where you can actually like leverage a part and have it do more than it can. I think that more offerings for flame retardant parts is going to be a really important aspect of it. A more reliable ceramic parts, like we talked about AM ceramics. I do think that's going to be the hardest to characterize, because right now a lot of AM ceramics, you're burning out a polymer. So now you're creating an unreliable matrix of ceramic part behind that may not actually be the same in each part, whether it's not mixed properly in the same ratio, or it just doesn't burn out of the same places the same way, collapses more in the X and Y and Z. So like better and more stable ceramic parts that are more useful, like technical ceramics that can come off of a printer, but also just making things like Ultim not only provided from like one supplier, for example. Like there's a lot more competition that does create variability, but making it so that more people have access to the technology in more places. You don't want suppliers making decisions on production just because they don't have it in-house, or they don't have a supplier in their vendor system who can make the parts they're looking for, or they're just not set up to produce with additive. So I think just, you know, more easier to use and more accessible versions of what's already out there, and more robust offerings is definitely in the future, on top of flame retardants and coatings.
Cool. So Suraj, there is another question here. Maybe I think you can answer. We keep talking about peak and Ultim, right? When you say high performance polymers, so immediately you know the advantages plus minus of each material. The question is, what other high performance polymers can be used in aerospace besides peak and Ultim? If it's not now, maybe in the future.
Yeah, no, good question. Very good question. I think mostly we use a lot of composites, you know, like carbon fiber reinforced thermoset composites. And if those are hard to replace easily with the other polymer composites, though there's a lot of work going on 3D printing of composites at the moment. And those are very much candidate along with the list which Chris and David just mentioned about. I mean, we're exactly looking at the same things. Similar things, you know, with that Ultim and all. And same way, PEK, PEKK, you know, we are looking into those composites too. But the thing is, in aerospace industry, many times primary and secondary structures are high strength or high stiffness. So you are forced to go mostly to metallics. And the polymer parts are there, you know, polymer composites with a sandwich structure to make a stiffener. Then we do use composite to replace aluminum sandwich panels and all the other. So, but be that said, polymer we do use in many places where, you know, the RF component or electronic components. But when it comes to secondary structures, which are where you use a lot of polymers, or the type of, which Chris just mentioned about LTM 9085 with different fillers, we do use. And there is a future for that. But my basic thesis is to bring additive manufacturing more in the trade space, so that we can use in our systems all the time. And that is, we have to cross that hump before we talk about future more and more. So I'm just trying to make sure we'll be realistic about it. We are exploring all that for future. At the same time, we have to start qualifying and flying that as much as we can.
Well, I have another list of 50 questions.
Right. Yeah.
But we are out of time.
Thank
so,
you.
Matt,
and my apologies.
Yeah, no problem, Suraj. Thank you for attending. Thank you all for attending. It was super interesting for me, and I'm sure for the audience.